Hey guys, this is the fourth part of my walkthrough on the SAT's math calculator section. If you haven't watched the first three yet, you can go back and watch those. Before we start, this video is sponsored by Prep Scholar. If you're looking for a test prep service, Prep Scholar is always the ones I recommend because their program was written by SAT experts. They have thousands of questions in their question bank that super closely emulate the actual SAT content, which I think is one of the most important things when you're studying. They are where I get a lot of my tips and tricks that I post on this channel, and they were definitely one of the reasons I was able to score 1600. So go check out the description below if you're interested for $50 off their SAT or ACT prep, or you can check out their new tutoring services that they offer. Alright, let's get into things. So now we have which of the following is an equation of a circle in the xy plane with a center of 0, 4 and a radius with an endpoint of 4/3, 5. So it's important to remember the circle equation. X minus h squared plus y minus k squared equals r squared. So the point hk is going to be the center of our circle, and then the radius will be squared on that side. That's important to remember. So we have our center at 0, 4. So our x-coordinate is 0, our y is 4. And since we use like the negative values of these, it would look something like that on our left-hand side. So these two are out because they're not negative. They forgot to kind of invert the coordinate of the center. Now we have to find our radius. Let's just draw a little circle thing for now. If we have an endpoint at like 4/3, 5, our circle is going to look like this. So the radius is just going to be the distance in between these 2 points. So we can use the distance formula to find the distance between these 2 points. So the way that works is you take your x-coordinates and your y-coordinates difference between them, square those, then square root that whole thing, and you'll be given the distance. And just looking ahead, we know that the value on this side is going to be the radius squared. And since we know that this is the radius, if we square that, or just take what's inside the square root, that'll give us the value we're looking for on that side. So if we take x, let's call this the second point and this the first point. So x2 minus x1, 4/3 minus 0, then square that. It's just going to be 4/3 squared. Then add that to y2 minus y1. That's just going to be 1 squared. So we have 16/9 plus, we'll call that 9/9. It's equal to 25/9. We can just rewrite 1 like that. And remember, that's our value for that side. But if you just want to double check, we could calculate the actual radius by doing 25/9 square root of that. And that's going to be equal to 5/3, which is the actual radius. But remember, we don't want, in this case, we want the 25/9 since we're looking for radius squared. All right, and I feel like we did a double check for that. You could go back if you wanted and make sure you did this step right. Okay, so now the equation above expresses the approximate height h in meters of a ball t seconds after it's launched vertically upwards from the ground with an initial velocity of 25 meters per second. After approximately how many seconds will the ball hit the ground? So this equation represents height. This is going to be like a quadratic, and if you think of a ball, it's going to be looking something like that as you throw it, which makes sense because we have a negative sign in front of this. So it's going to be like a negative quadratic. And it's not as important as with linear equations to know what each of these coefficients represent, but it's important to know kind of overall how to graph these. So this is kind of like a red herring value. We're looking for the time that this ball hits the ground. So at the beginning it's at the ground, and then we're looking for this other point here. So in this case, this axis is h, this one's t. So we can just solve this equation when h equals 0, because that's going to be when this value is 0. That's when it hits the ground. So if we take that, you can see we have a much more solvable thing here, because we can factor out a t. We see that one of our solutions to get this equal to 0, t would have to equal 0. And that makes sense because we know the ball starts at the ground. And the other one we can get by solving this inner equation to get this equal to 0. So if we subtract both sides by 25 and then divide by negative 4.9, we get about 5.1, or the closest one we have is 5. So I'm good with that. And then, good way to check this one is just plugging this value of 5 in for t and seeing if you get a value of 0. So we would have 5 times 5 is 25 times negative 4.9 plus 25 times 5, we get 2.5, which is pretty close to 0, especially compared to what these other ones would give us. Katerina is a botanist studying the production of pears by 2 types of pear trees. She notices that type A trees produce 20% more pears than type B trees did. Based on her observation, if type A trees produced 144 pears, how many pears did the type B trees produce? So the type A are going to produce 20 more than type B. So A is going to be 120% times B. In decimal form, that's 1.2 times B. So then if A produced 144 pairs, then we can just solve for B to figure out how many it produced. If we divide by 1.2, on both sides, we get that the type B tree produced 120 pairs. And to check this, let's just make sure this value makes sense, because it's easy to like flip this equation around. So type B is 120, type A is 144. We know that type A needs to be greater than type B, so we are good to go, at least in that regard. A square field measures 10 by 10 meters. 10 students each mark off a randomly selected region of the field. Each region is square and has side lengths of 1 meter, and no two regions overlap. So we have something that looks like this, but it's a 10 by 10 grid. The students count the earthworms contained in the soil to a depth of 5 centimeters beneath the ground surface in each region. The results are shown in the table below. So they're just digging under these plots to get some worms. Which of the following is a reasonable approximation of the number of earthworms to a depth of 5 centimeters beneath the ground surface in the entire field? So in this case, the 5 centimeter depth is kind of the red herring here, because we know they're being measured 5 centimeters deep, so we don't really have to pay attention to that value. Let's look at this little table to see if it helps us. So like between 107 and 176 earthworms are found in each one of these little tiny patches that makes up the big patch. So we're looking just for an approximation. So it looks like they're calling the average of these values about 150, which makes sense. It's close to there. So we're looking for basically the difference between one of these little squares and the big whole entire plot, because we're looking for the entire field given just one tiny little region that they searched. If we drew a 10 by 10 field, the area of that field would be 100 little plots. So that means we can just multiply the 150 number of worms by 100 different plots. There are 150 worms per plot, and that should give us an estimate of the total amount of worms in the patch. We get 15,000 worms. I have to say, I'm not a fan of worms. I would not like this, but good for them. And to check this, just make sure you're solving for the right value. It's a 10 by 10 meter field, and these regions are close to 150 worms, so I think we're pretty good with this one. If the system of inequalities is graphed in the xy plane above, which quadrant contains no solutions to the system? So if you want, you can graph this with a graphing calculator if you have one, but honestly, it might be easier to just do this by hand. So for graphing inequalities, you can just treat it like a normal equality, like this sign wasn't here, and then we can add that later on. If we have our y-intercept of 1 and our slope is 2, so it's going to go up 2 over 1. That's our little estimate of the first line. Then the second one, our y-intercept is going to be -1 and a slope of 1/2, so it's going to be up 1 over 2. So that is our little second line. We got to find out whether the top of the line or the bottom of the line is going to be shaded. Y is greater than or equal to this expression. So that means the y has to be greater than this line. So like if you had it here, the y would have to be a little over. So we know that this region is the one that's shaded for the first line. And we don't really care about like dotted lines versus solid lines. We'll just pretend that they're solid for now, unless that's causing a problem for us later. So this one would be like a dotted line since it doesn't have the greater than or equal to. I don't know if that really matters here. So in this case, it's also greater than that line. So this one would also be shaded above the line. I'll just shade this in a different direction so it's easier to see. But we're looking for the value where these two overlap. So in this case, it's only this region and beyond, where both of them are shaded at once. Kind of destroyed option D here, whoops. But there are no points in the fourth quadrant where both of them have solutions. We have solutions for the second of the equations in here, but both of them have to be for the system of inequalities to have a solution. So in this case, quadrant 4 would be our answer. And to check this, maybe do graph it on your graphing calculator or just try it again. Make sure to note the direction of these lines and get your slopes approximately right, and you're good to go. All right, now this one's kind of terrible. For polynomial p of x, the value of p of 3 is -2. Which of the following must be true about p of x? So this one's kind of relating to long division in a way, like whatever that chapter of Algebra 2 was. Basically, it's saying if we plug in a 3 for x, we get a non-zero answer for our y value. So in this case, it's like if we divided the whole thing by x minus 3, since x equals 3 is a solution, we'd get -2 as like the remainder. And there's this equation. It's kind of terrible, but it might refresh your memory on this form. So if you divide by x minus the number in this parentheses, you get basically another polynomial and like your remainder over that same thing that you divided by. And that's just like a thing to remember, but it's also kind of the only one that makes sense, because if these were factors, that would mean x minus 5 or x plus 2 would give us a y value of 0 since they're factors. And having p of 3 give us -2 doesn't tell us any of these things. All we can really say is that the remainder is -2. Now this is a very mean one. Which of the following is an equivalent form of the equation of the graph shown in the xy plane above, from which the coordinates of vertex A can be identified as constants in the equation? here's the key. So there are multiple ways to represent quadratic equations. This standard form that they give us is one of them. There's also a thing called vertex form, where the vertex of the equation is represented like in the actual equation. And then you can also represent it with like its roots represented. So here we have like -3 and 5. So that we know we get a y value of 0 at the points -3 and -5 to represent the equation. We can also figure that out by factoring that standard form, but it doesn't allow us to see right off the bat where that vertex is, which is what the question is asking for. So we want to represent this in vertex form, and we can do this by completing the square if we want to, or we can just trust that that answer is right, because this one doesn't look like the form for a polynomial. We can try expanding it out though. I guess it is, but that's not like a typical form that you see. So if we complete the square here, assuming that y is 0, try to create this in a squarable form. So like x2, and we do this by dividing by 2 and squaring this coefficient right here. So we'd have -2 divided by 2, so -1 squared, +1, then -15. And then because we added this +1 here, we also have to add it on this side. Now we can group this together, like we can factor it to get x minus 1 squared, -15, and then bring that 1 to the other side, and we get 0 on that side. So we get a solution like this, which matches with that when y is 0, and then we can deduce that that's our equation. So in this case, very tricky. We get 3 different equivalent forms and 1 incorrect form of this standard form equation. We just have to parse out which thing we're supposed to be focusing on. So that's it for this part. Join me next time where I'll go through the final questions of this calculator section. Until then, thanks for watching. Be sure to like and subscribe, and see you soon.